There's a document that sat classified for almost 40 years after the war, and for most of that time, even physicists who worked adjacent to the project had no idea it existed. It wasn't about how to build the bomb. It wasn't about yield or design or any of the engineering questions that dominated our work at Los Alamos. It was a calculation about whether, once we detonated the device, the reaction might not stop with the bomb at all, whether it might continue uncontrolled into the atmosphere itself and keep going until there was no atmosphere left to burn. I want to walk you through how that calculation came to exist, why it terrified the people who ran it, and why even after we had an answer we trusted, almost nobody outside a very small circle was ever told. It started in the summer of 1942, before Los Alamos existed as a laboratory, back when much of the theoretical work was still being done at Berkeley. I was running a summer seminar there, a small group of theoretical physicists, the kind of gathering where you invite people you trust to think freely, without worrying yet about engineering constraints. Edward Teller was in that group, Hans Bethe was there, Robert Serber, Emil Konopinski, John Van Vleck, a handful of others. We were meant to be working through the basic physics of a fission weapon. How much material, what configuration, how the chain reaction would actually behave once it got going. Teller, who had a genuine gift for finding the question nobody else had thought to ask, raised something that stopped the room. We were already discussing fission bombs, but Teller had been thinking further ahead, toward the possibility of an even more powerful weapon, one based on fusion rather than fission, what we'd eventually call the hydrogen bomb, though it was barely more than a speculative idea at that point. And in thinking about the temperatures a fusion reaction might reach, he asked a question that had nothing to do with weapons design and everything to do with basic physics. At those temperatures, could you ignite a fusion reaction in the nitrogen nuclei in the surrounding air itself? Could the bomb, in other words, set the atmosphere on fire? It sounds almost absurd, stated plainly, and I understand why, decades later, it gets treated sometimes as a kind of urban legend, the sort of thing that sounds too dramatic to have actually been a serious scientific question. But it was a serious question precisely because the underlying physics wasn't obviously impossible. Nitrogen nuclei can, in principle, fuse under sufficiently extreme conditions, and a nuclear weapon was going to produce temperatures higher than anything ever created on the surface of the Earth, if only for a fraction of a second in a very small volume. The question wasn't whether fusion of atmospheric nitrogen was theoretically possible under extreme enough conditions. It clearly was at some temperature. The question was whether our device would reach anywhere near that temperature, and whether, if it did, the reaction could actually sustain itself and spread outward through the atmosphere, rather than simply flaring out in the immediate vicinity of the blast and dying. Teller ran through some rough numbers that summer, and by his own account, got a result that alarmed him enough to bring it directly to me. I remember the feeling of that conversation clearly, even now. You don't often have a colleague walk up to you with a calculation suggesting the project you're both about to spend years of your life on might, in the worst case, end in something far larger than a single destroyed city. I did what I think any physicist in my position would have done. I didn't dismiss it, and I didn't panic either. Panic isn't useful in front of a piece of mathematics, useful or not. I took it seriously enough to interrupt my own plans. I got on a train to go find Arthur Compton, who was overseeing the broader project at the time, spending part of that summer at a lake in Michigan. I found him there and laid out what Teller had shown me, and I remember Compton's response mattered to me a great deal because he didn't brush it aside either. He understood immediately that if there was even a real possibility the weapon could ignite a self-sustaining reaction in the atmosphere, The entire project needed to stop until we knew for certain, one way or the other. Compton said later that he'd decided if the probability of igniting the atmosphere was anything more than roughly 3 in a million, the project simply could not proceed. Better, he said, to accept the risk of Nazi Germany getting the bomb first, than to run even a small chance of destroying the world in the process of stopping them. That's the part of this story that I think gets lost when people repeat it secondhand. It wasn't recklessness that led to the calculation. It was the opposite. The moment the possibility was raised, seriously by people with the mathematical standing to be taken seriously, the entire project effectively paused on that single question until it could be answered properly. The task of answering it fell largely to Teller, along with Emil Konopinski and Cloyd Marvin, working through the detailed physics of what would actually happen. The calculation is not simple, and I won't pretend I can walk you through every step of it here, but the shape of the argument matters. You need to know the temperature the fission device would actually produce at its core. You need to know the cross-section for nitrogen fusion at that temperature, essentially how likely 2 nitrogen nuclei are to actually fuse when they collide, rather than simply bouncing off each other, which for most nuclear reactions at these energies is the far more common outcome. And critically, you need to compare the rate at which energy would be produced by any fusion that did occur against the rate at which that energy would simply radiate away into the surrounding, much colder atmosphere, cooling the reaction faster than it could spread. That last part turned out to be the crucial piece. Nitrogen fusion, even under the extreme temperatures a fission bomb could produce, has an extraordinarily low cross-section at those energies. The nuclei mostly just don't fuse, even when they collide, because the reaction requires overcoming an electromagnetic repulsion between 2 positively charged nuclei that fusion at those temperatures barely manages to surmount, and the volume of superheated air immediately surrounding the detonation is small, cooling rapidly as it expands and radiates energy outward. The team's calculations showed that any nitrogen fusion that did occur in the immediate fireball would release energy far too slowly and lose heat far too quickly to the surrounding unignited air to ever become self-sustaining. The reaction, mathematically, was destined to sputter out within a minuscule volume rather than propagate. Teller and Konopinski wrote up the result formally, and it eventually became a Los Alamos technical report, LA 602, finished properly in 1946 after the war, once there was time to formalize the wartime calculation with more care. It concluded with what the authors described as a comfortable margin, that igniting the atmosphere was not possible under any conditions we could produce with the weapons we were building. I believe that conclusion. I want to be honest about that because there are people who've suggested over the years that we proceeded to Trinity carrying real doubt about this question. And that isn't how I remember it. By the time we assembled the device in the New Mexico desert in July of 1945, the atmospheric ignition question had been closed for years, checked by more than one physicist, using more than one method, and every version of the calculation came back the same way. The margin wasn't thin. It wasn't a coin flip we talked ourselves into accepting. The physics of the cross-sections and the radiative cooling made the outcome about as clear as anything in a genuinely novel piece of physics can be. So why did we keep it from the public for so long? I've thought about this question more than people might expect, because I understand exactly how it looks from the outside. It looks, on its face, like the kind of thing that should have been the first fact released, not the last. Proof that we'd been responsible, that we hadn't simply gambled with the planet. Part of the answer is the most mundane one. everything connected to the bomb's actual physics was classified during the war as a matter of course. And that classification didn't distinguish between calculations that were frightening and calculations that were reassuring. The atmospheric ignition report described in some technical detail the behavior of nuclear reactions under extreme conditions, cross-sections, energy transfer rates, the kind of information that, however reassuring its conclusion, still touched directly on the physics of weapon design. The security apparatus around the project treated it the way it treated everything else: seal it, restrict it, decide later. But I think there's a second reason, one that has less to do with formal secrecy rules and more to do with how the people who ran the project thought about public understanding at the time. Explaining the atmospheric ignition question honestly to a public audience in the middle of a war meant first explaining that the possibility had been considered seriously enough to require a formal calculation, and only then explaining why the calculation came back negative. It is very difficult to introduce the first half of that sentence to a frightened public without the second half getting lost entirely. Compton himself, in later years, seemed acutely aware of exactly this problem, that describing a worst-case scenario, even one that had been ruled out with real confidence, risked being remembered only for the worst case and not for the confidence. There's also, I think, a discomfort that doesn't get discussed enough, which is that the calculation forced an admission most of us weren't eager to make out loud in 1945, that we had built something whose ultimate physical limits were not, at the outset, fully known to us. We were confident in the atmospheric ignition answer specifically. We were less confident, in a much broader sense, about everything the weapon might set into motion once it left our hands. Politically, historically, in ways no calculation could resolve. Talking too openly about the one physical question we had actually managed to close off might have invited exactly the harder questions we had no similarly clean answers for. The report stayed classified for decades. It wasn't declassified and made available to historians and the public until 1973, nearly 30 years after Trinity, by which point most of the men who had actually run the calculation, myself included, had spent the rest of our lives answering, in one form or another, for a decision that history had already judged in every way except this one narrow technical one. I've always thought this story deserved to be told more plainly than it usually is, because it captures something true about how careful the physics actually was, even in the middle of a project that history remembers, understandably, as reckless. We did not build that weapon and hope for the best on the question of whether it would consume the atmosphere. We stopped, we calculated, we checked the calculation more than once, and only once the mathematics closed the door firmly did the work continue. The tragedy of the bomb was never that we failed to ask the hardest physical questions. It was that even the most careful physics in the world could never answer the question of what it would mean, once built, for us to have it at all.